Hi, this is Maggie from Design Code Debug Repeat. Welcome to the channel. If you know how to blit one surface onto another in Pygame to create a composite image, but you're scratching your head over the Pygame blending modes, or wondering how to implement cool effects like a fade-in or inverting an image, then this is the video series for you. Today we're going to start looking at each of the blending modes, explaining how they work, illustrating with examples and graphics, and we'll talk about what sort of effects you can accomplish with each mode. We'll finish in additional videos because there's a lot to see. Let's get right into it. When you create an image in Pygame, a background or a sprite for example, you're creating a Pygame surface. You start by giving your surface a size, a width by a height, and that is the number of pixels across and the number of pixels down it will be. You might read the image from a JPEG, PNG, or GIF file into a surface, and then the surface will have the dimensions of the image. Each pixel of the surface stores information for a color, either RGB, a red component, a green component, and a blue component, or RGBA, red, green, blue, and alpha, or transparency. Each of those values is an integer between 0 and 255. 0 is none of the color for the RGB channels, or full transparency if it's the alpha channel, and 255 is the full amount of the color, or full opacity if it's the alpha channel. If you are using the alpha channel, this is sometimes referred to as per pixel transparency to distinguish it from other ways of setting transparency in Pygame. Setting a transparency value for an entire image with set alpha, or specifying that one color in an image should be transparent with set color key. With per pixel transparency, each pixel in the image has its own transparency value. If you want per pixel transparency control, you need to specify that when you create the surface. Either pass the pygame.src alpha flag when you create the surface, or send the convert alpha message to the surface after you've created it or loaded it in from a file. If you want to composite two or more surfaces, and you do or you wouldn't be here, you can blit one surface to another. Blitting copies the pixels from one surface onto the other surface. Here's the Pygame blit documentation. When we blit, we're sending the blit message to the surface that we're going to blit onto. That is called the destination surface. That surface is referenced by the variable before the dot. The first argument, source, is the surface we're copying onto the surface receiving the message. So in this code, screen.blit working 00, the surface called working is being copied onto the surface called screen. Screen is the destination, and working is the source. The next argument, dest, is the left top coordinate on the destination where we want to start copying the pixels from source to destination. 0, 0 is the left top, but we can copy to any part of our destination surface. We then have two optional arguments. The area is the part of the source that we want to blit, and special flags is where we can specify a blending mode. Let's start with the default blending mode called Standard Alpha Compositing or Straight Alpha Blending. If you don't include an optional blending flag, the default is used. With the default blending mode, the alpha of each source pixel is normalized or converted to a value between 0 and 1 by dividing it by 255, the maximum value a pixel can hold. The R, G, and B components of the color are each multiplied by that normalized alpha value. Now the RGB components of the destination pixel are multiplied by 1 minus the normalized alpha value, and then the two products are added together. That resulting pixel will be a blend of the source and destination pixels if the source alpha was less than 255. The alphas are also blended according to a slightly different formula. We add the source alpha to the destination alpha multiplied by 1 minus the normalized source alpha. Let's look at an example with illustrations. This is blend examples default add.py, and I'm going to uncomment examples as we go. Also note there's code in here printing specific pixels for illustration, which I've left in when I uploaded this to my GitHub repository. So you can run this and look at exactly how the calculations work out with specific pixels. In all of the examples, I'm going to blit onto a surface I've created called working, which is created with the src alpha flag. Again, that means we have a per pixel alpha on that surface. At the end of the program, I will blit that onto the screen and flip the display. The surface created with pygame.display.setMode, which I've called screen, uses different compositing algorithms. So always blit to a working surface if you want to create compositing effects with blending modes, and then blit that surface to the screen when you've finished creating it. In the first example, I'm blitting a background, which is an image of a dystopian city, and then I'm blitting a blimp over that. I loaded both of these images in from files. The background is a JPEG, and the blimp is a ping with transparent pixels around the blimp image. The pixels happen to be white, but they're completely transparent, color values of 255 and an alpha value of 0. I send both surfaces the convert alpha message after I load them in. And here's what the image looks like with the background, which is the same size as the window, blitted to 0, 0, and the blimp blitted to 100, 100. Again, using the default blending mode. What we see is the opaque or visible pixels of the blimp completely replacing the pixels of the original image. But the transparent pixels of the blimp image do not appear to be blitted at all, because we're seeing the original destination surface pixels of the dystopian city. You can see how that works out with the math. I printed the pixel values from each surface that will be composited together and the result, one set for an area with full opacity, and one set for an area with full transparency in the blimp image. Let's start with the opaque pixels in the source. If we have a destination pixel that's 139, 163, 167, and 255 for the alpha, and we're blitting onto it a source pixel that's 242, 233, 202, and 255 for the alpha, the result is the 242, 233, 202 pixel with the 255 alpha. If you look at the math, 255 divided by 255 is 1. That's the normalized alpha value for the source pixel. And 1 minus 1 is 0. So all of the source color values are multiplied by 1, and all of the destination color values are multiplied by 0. So the resulting pixel has the RGB values of the source. Now let's look at a transparent pixel in the source. If we have a destination pixel that's 137, 161, 165 with a 255 for the alpha, and we're blitting onto it a source pixel that has a 0 alpha, it doesn't matter what the color is, but in this image it's 255, 255, 255. Then our multiplier is 0 over 255, or 0, for the source pixel, and 1 minus 0, or 1, for the destination pixel. So we get a result that is the same as the original color on the destination. But what about when the alpha is something between 0 and 255, neither fully transparent nor fully opaque? I've created a surface called Searchlight, although it looks more like a lens flare. It's an all-yellow surface, but I've got full opacity in the center, and then the opacity reduces to 0 at the edges. When that is blit over the background and the blimp, you can see a yellow haze over the entire image, complete yellow in the center, but clear at the 4 corners. Let's choose a location somewhere in the haze. We can look at the same pixel we looked at before. The destination pixel is 137, 161, 165, with 255 for the alpha. That pixel is at 220, 102 in the background image. The pixel at 220, 102 in the Searchlight image is 255, 255, 0, yellow, with an opacity of 160. After it's blit to the working surface, the pixel at that location is 211, 220, 61, with an opacity of 255. Let's just look at the calculation for the red component of the pixel. The calculation for all of the color pixels is the same, just substitute in the different values. 255 times the normalized alpha, so 255 times 160 over 255. The 255s cancel out, and that's 160. Plus the destination red value, 137, times 1 minus the normalized alpha, approximately 0.37. That's 51. 160 plus 51 is 211. And you can see what this works well for, blitting an image with transparency onto another image, as I've blitted the blimp onto the cityscape, or blitting a slightly transparent effect over an image or part of an image. Remember to send the convert alpha message to every surface you read in from an image file, or if you're creating a surface, like I create the Searchlight image, make sure you pass the src alpha flag to the initializer. The blit documentation lists 3 add blending modes: blend add, blend RGB add, and blend RGBA add. Add means that each component of the pixel values from the source and destination surfaces will be added together without exceeding the maximum value of 255. Blend add and blend RGB add are the same. They add pixels without considering the alpha channel, meaning the alpha remains whatever it was originally on the destination surface. When you create a surface, its pixels are 0, 0, 0 with an alpha of 0. So if you blit to that in a mode that doesn't consider the alpha, like blend RGB add, you're going to be left with all transparent pixels, an all black surface. I'll blit my background to working with blend RGB add, and you can see how much more black could that be? And the answer is none more black. But let's change the destination surface working to be black with a fully opaque alpha channel, so 000,255. And now when we blit the background, it comes through exactly because the destination had 0 in each of its color channels and a fully opaque alpha channel. So we added each color in each source pixel to 0, giving us the source color pixels, and they remained fully opaque. Let's blit a dark gray over that. I have a surface called filter surf, and it's being filled with 100, 100, 100. It has an alpha of 0. It doesn't matter what the alpha is because the alpha on the destination surface is 255, and that's not changing. You can see that lightens the image because we've added the same amount, 100, to each pixel. Now, I have one more image. It's called Spotlight. It's all black with a dark gray circle in the upper left. Black, remember, is 000, so when we add that to a pixel, it won't change the color of the pixel. But the dark gray circle has pixels with values 100, 100, 100, just like before. When I blit that over the background image, the only part that's lightened is the part where there are pixels with a non-zero value, the dark gray circle. Let's look at an example of blend RGBA add. This works the same as blend RGB add. The pixel color values from the source are added to the pixel color values on the destination, but the alpha channels are also added. Let's reset working to its original state, black with a transparent alpha channel, or all zeros. We'll start with blitting the background to the black transparent working surface. Now this time the blit works. Recall that with blend RGB add, it did not because the alpha on the destination surface was 0, and blend RGB add keeps the alpha on the destination surface. But with blend RGBA add, the alphas are also added, so our fully opaque background image was copied exactly to the working background, including the alpha channel. We can blit the spotlight, and we get the same effect as before. This still works because for the alpha channel, we're adding 255 plus 255. Since we can't go over 255 for any value, they remain at 255. The pixels are already fully opaque. We can't make them any more opaque. So what does adding the alpha channel bring to the party? We can use the alpha channel to layer brightness, for example, with two spotlights that overlap. I'm going to reuse my spotlight surface and create a 100 pixel by 100 pixel surface that is filled with a 100 pixel diameter yellow circle with a consistent alpha of 60 over each circle pixel. The surface around the circle has an alpha of 0, so transparent. Then I blit that together with another circle onto a working surface called filter surf. The filter surf is completely transparent and black. So when I blit with RGBA add, it will not contribute to the values of any of the pixels being blit. I will blit one spotlight onto it, and then another spotlight partially overlapping. Where the spotlights overlap, we get a pixel that is 255 plus 255 for red, or 255. 255 plus 255 for green, or 255. And because I gave this a blue of 100, it will have 200 for the blue component. So a color very close to white, but more yellow than white, a very light yellow. And the alpha at the overlapping area will be 120. The alpha where the spotlights don't overlap is still 60, and the color is still 255, 255, 100. I then blit the filter surf over our background. And you can see the effect is two yellowish transparent spotlights that are lightening the surface behind them, and then an overlapping area that is a much lighter yellow, brightening the overlapped area even further. When we combine the pixels with the pixels from the original background image, we use the default blitting mode. We don't want to add here because then we'd end up with basically a blindingly white area. We only use the additive blending to create the overlapping spotlight surface. We then want that to combine according to the alpha values with the underlying surface, the dystopian city. Now, I hope you found this interesting and useful. There are basically two components to these blending modes. One is understanding mathematically how they're combining the pixels, and the other is understanding in practice what that looks like. As you practice with it, you will develop an intuitive sense of what different combinations of color and alpha values look like, and also how they combine with other RGBA colors both additively and with the default blending mode, and this should help you understand how to use them to produce different effects. Let's do a quick quiz to get you started practicing with these blending modes. You can pause the video and think about your answer before I reveal the correct answer. On the left is the destination surface created with dest equals pygame.image.load background.jpg.convert alpha. No tricks, it's the same full opacity JPEG from the video. In the middle is the source surface created programmatically. The pygame.src alpha flag was passed to the initializer, and then it was created to be all yellow pixels, but with full opacity in the center, fading out to complete transparency at the corners. And here's my results surface on the right, created with dest.blit source 00 and then a blank. In the results surface, we can see the background image through a yellow haze. What goes in the blank? Is it A, nothing, the default blending mode, B, special flags equals pygame.blend_RGB add, C, special flags equals pygame.blend_RGBA add, or D, this cannot be achieved with what we've learned in this video. Pause and work it through. Did you get it? The answer is A, the default blending mode. The default blending mode calculates the color value of each pixel according to the pixel alpha values in the source. Because the pixel alpha values vary in the source, we're getting varying degrees of yellow mixed with our destination pixels. From fully yellow in the center, where the source is opaque, to fully original destination pixels at the corners, where the source is transparent. Ready for another? On the left is the destination surface created with dest equals pygame.image.load background.jpg.convert alpha. This is the same image from the prior question, and again, it's a fully opaque image. In the middle is the source surface, which is also loaded in from a file, with source equals pygame.image.load spotlight.jpg.convert alpha. Now, this is a JPEG, meaning it has full opacity throughout the image. A PNG might have a different alpha value for each pixel, so if we load a PNG and then send it the convert alpha message, our surface will have those different alpha values for the pixels. But a JPEG is always fully opaque. This spotlight image is mostly black with one circle of dark gray, 100, 100, 100. Now we're combining these again with dest.blit source 00 blank. What goes in the blank? Is it A, nothing, the default blending mode, B, special flags equals pygame.blend_RGB add, C, special flags equals pygame.blend_RGBA add, or D, this cannot be achieved with what we've learned in this video. Pause and work it through. Did you get it? If you answered that this could use either add mode, B or C, then you're a blending modes expert. You're correct. If you answered one or the other, you did great. The default blending mode will not give us this result when combining these images because the source is fully opaque, meaning the source pixels will replace the destination pixels. But the add modes will add the black 0 color values to the color values in the destination, making no change to those destination pixels. And the add modes will add the 100 values from the gray circle to the destination pixels in the circle, making them appear lighter. If we use RGB add, then the destination alpha of 255 is used. If we use RGBA add, then the destination and source alphas are added together. Since they're both 255 and no value can exceed 255, it's still 255. How about one more, a challenge? You haven't seen this one. So again, for the destination, I've loaded the background image from a JPEG and sent it the convert alpha message. No tricks. And for the source, it's the blimp image, which is a PNG, and I've loaded that and sent it the convert alpha message. Remember that the blimp is fully opaque where there are pixels in the blimp image, and the pixels around the blimp are white and fully transparent. So 255, 255, 255, 0. And the result after sending the destination.blit source 100, 100 blank message is the background with a rectangular white block starting at 100, 100, and inside the block is the blimp, but in the originally darker areas of the blimp, it's transparent. What goes in the blank? Pause and work it through. So what do you think? What's going to make the transparent pixels opaque and make the dark pixels essentially transparent? If you said either of the add modes, answer B or C, you're correct. With RGB add, remember the destination alpha is used. That's full opacity, 255. So the white pixels, which are 255, 255, 255, are added to the destination pixels, and we'll get values over 255, but 255 is the max. So those transparent pixels are all now showing white. If we use RGBA add, then the alpha values are added together, so 0 is added to the 255 for the transparent pixels, and we still get 255. And the color channels are still added together, and we still get 255. What about those transparent areas of the blimp? It's just like the spotlight image, where the black areas have no impact in the add blends. The pixels on the bottom of the blimp are very dark, either black or very close to black, so they might lighten the background pixels a little when we add them, but if they're 0, they have no effect at all. So the effect is we're seeing the background through the dark parts of the blimp. I hope you enjoyed the video and the quiz. Stay tuned for more blending modes in an upcoming video. As always, have fun and keep coding.